Good afternoon, everyone. Welcome to Sharcnet General Interest Seminar. Today, we'll talk about the new features and the protocols provided by OpenMP 4.0 and the latest 4.5 specifications. My name is Jamie Hu, and I'm a Sharcnet HPC consultant at University of Waterloo. We'll start with an OpenMP overview, then we'll introduce the three models: the task constructs in OpenMP, SIMP constructs in OpenMP, and the device models in OpenMP. There are many nice online documentations. If you are interested, you can check the references I listed in the last slide. So as an overview, or simply speaking, OpenMP is an application programming interface for writing multi-threaded applications. So it includes a set of compiler directives and lab routines for parallel application programmers to run on shared memory machines. So the API applies to both C, C++, and Fortran programming languages. It's still C, C++, and Fortran are the dominant programming languages in science and engineering computing. OpenMP takes the same P-thread concepts, but it's much simpler in coding side because it's basically a high-level application, and it's easy to implement. So basically, it built on top of your sequential code, often use a few OpenMP directives can achieve the parallel goal. So it's widely applied to loop parallelizations. And it's something that maybe you know the other parallel approach for distributed memory architecture, the message passing libraries. So message passing libraries where you need to start from the beginning, and a totally different algorithm you have to use. OpenMP actually built on top of a sequential code, so it's easy to implement. And then it's standardized support by all the compiler providers. And now it has been extended to different applications. So that's what we'll talk about: the vectorizations and the heterogeneous device, and also the task models. Here is a simple explain of the programming models in OpenMP. It's used a fork-join model of parallel executions. So basically, your code starts with a sequential code and run, say, on one CPU. And then in your code, you will use the OpenMP directives. The first one will be the start of parallel region. At this point, so the master thread will create a team of threads. And then all your code on the parallel region will be executed in parallel by different individual threads. And then at the end of the parallel region, all the threads will complete or finish its job, its task, and then it synchronize, and it terminate. And then you code back to a sequential code. So this process will repeat maybe many times, depends on the applications. So basically, the code is not a full parallel code. So it's basically a sequential code, and then at some part, your code will run in parallel use a team of threads, and then your code may back to sequential code, and then use back, and then will start in parallel again. So that's pretty much is like a partial parallelization. Mostly is a local parallelization, or you parallelize the most of the time consuming part of your code. So right now, I think most of the applications were based on OpenMP 3.0 or 3.1. We had an introduction to OpenMP some time ago, and we also had OpenMP summer course in last a few years. At that time, and we talk about some details about OpenMP. So the contents, basically, we can put together here. So the OpenMP's constructs is basically fall into 5 categories. So the first important thing is the parallel region. So that's all the starting point of OpenMP. And then the most important thing is the worksharing constructors. And to parallel apart, the workload is shared by a team of threads. And all OpenMP involves the data environments. So what type of data is shared, what type of data are private. So that need to be dealt correctly. And then is the synchronization. So that's the key point to make sure the final result is correct. And there is no data risk issues, and there is no any problems in your final results. And you can use a few runtime functions or environment variables in your code to make sure it's under control. So this is the basic thing, and all those concepts and all those implementations are applied to both Fortran and C++. So here is a summary for the type of worksharing constructors. So the main part is for the for loop or dual loop. So it's basically share the iterations of a loop. So that's also the big part of OpenMP. If someone actually good in MATLAB, maybe MATLAB actually take the same approach, they call the path 4. It's hope the systems and to do the job for you automatically. So that's the major part. And then there's a lot of constructor called sections. So this one we sometimes can call it a functional parallelism or task parallelism approach. It basically breaks work into separate sessions, and each session depends on workload, maybe not exactly the same. And each session is executed by one thread. By doing so, it also let your code, each thread run different part, and there's no overlap there. And OR is basically run in parallel to speed up the performance. And then there's a constructor called a single, and put in a worksharing constructor. This basically used in central part, so you have no way to parallelize it. For example, you have data risk issues or whatever difficulties. And then you just let that part. You still have a team of threads work for you. However, only one thread actually do the job and make sure the result is correct. So this is a simple slide to show a motivation to use OpenMP. And the example is a simple loop. So the sequential code, you have a loop and to do whatever here, for example, to add, to do the sum of an array. And when you come into run in parallel for this type of simple loop, and you simply use the parallel region OpenMP parallelism constructor. So the syntax is programmer in C is OMP parallel. Here it create a team of threads for your job to do. And each thread will have its unique thread ID. And you will know, you can get how many threads in my team. And then you can basically hard coding it, say each thread do what part. And you can basically change the index in your loop. So here, this code will allow you to actually run in parallel. And then when you have a work sharing constructor like the for or do loop in Fortran, it makes the coding much easier. So you simply use the OP4, and then the compiler will know it, and the compiler will try to do the best job to divide your loop among a team of threads. And the threads will do one part of your loop. And overall, a team of threads will parallelize it or speed up your computations. So let's the simple one. So you can see from here, it's basically sequential code. What you need to do is to add your OpenMP directives to your existing sequential code. Okay. So here is a simple example. Calculate pi because it's simplest and it's actually has real meanings and can use it to explain the parallel programming. So if we take the approach, say calculate pi using numerical integrations, so mathematically you always have different approaches. So one for the approach, you can actually basically as a calculator the area, so among these regions, right? So the more beans you cut the more small number of beans, the better results you'll get. So what it in sequential code is just simple. You have some number set up, and eventually you add the sum in. It's just one loop, one for loop. You calculate each will do the sum, and finally you add the sum together. You get the results. So the same code, if we want to apply OpenMP to run it in parallel, the code is straightforward. So here is a sample code. Calculate pi use OpenMP with the work sharing loop constructor and the reduction. So OpenMP comes with a header file. It's basically define lab routines or the environments. So there's a header file you need to include to your code. And then others are basically exactly the sequential code you have. And then what we want to do, basically we want to parallel this for loop. And then here, basically all start with program OMP parallel. So this basically, at this point, it creates a team of threads. And here, starting from here, you start a parallel region. And we do the loop, we use the for the work sharing, and it basically break your loop to fit to the number of threads. So the compiler will try to do the best job if it's even, and hopefully each thread will get the same node, same workload. If it's not, it will try to have the iteration index divided by the number of threads. However, the last or left will be picked up by the last thread. And then we will do the job, and finally the code is this simple. The other example, I want to show the sections when you may like to use it. So for example, if I have a code, you have a sequential code, something like we used to say you use a case, the options, say in your type of C code. Here I basically say if I use 3 loops, And in this case, each loop will do whatever you want to do. And you can use a case, and what case will do what, and you run it in sequentially. And then in OpenMP, you can use hard code, still use case. You can get a thread number, and each different thread number to work on a loop. And then more simple thing is you can use the sections. Here you start with OpenMP, and then you work on sections. And then each section is actually one section will be run by one thread. So in this case, it's not the whole thread work on one loop. It's actually one thread work on this, another thread work on another one, a third thread work on a third one, for example. And in this case, your whole job is not done by one CPU, by one thread. You're actually by a team of threads. Well, use it or not, it depends on your application. If, say, all the runtime for the loop roughly equal, this will work as same as good as the worksharing for loops. Okay. Now, not all programs have simple loops. The OpenMP can parallelize. So there are many situations it's not a simple loop thing, although loop is the dominant thing in scientific computing. So consider this type of situations. For example, if we are working on a linked list. For linked list, we don't know how many elements in a list. So in the programming side, we always start from the head. And then we use a while loop to say we'll work on the, whatever the work need to do on that list. And then it keep moving to the next until the end of the list. So in this case, there is no count, so you cannot use this type of application in a loop structure. So that's something the existing OpenMP cannot do, because OpenMP are typically working to parallelize loop. The other one example is for recursive applications. So for example, these simple Fibonacci numbers. So the function is basically call itself, and the main code is call itself. There's no loop structure here. So this type of recursive applications cannot be done in OpenMP before. So because this type of application and the OpenMP community want to have this extended to more widely applications. So this was motivated to actually apply the OpenMP to be able to work on this type of problems. So this comes with the task. So what are tasks? So tasks are independent units of work. So sequential code, we can say, well, each part of your code will work on for some purposes, or is tasks. And then you have many things to do in your code. So each task are composed of code to execute, and also you have some data to compute with. And then if somehow we can say later each thread pick up one task, and then if we have a team of threads, and then by working on team of threads working on each on different tasks, and then we can parallelize it, and eventually the goal is to decrease the runtime for your code. So the tasks are assigned to perform the work of each task. The threads are assigned to perform the work of each task. So the thread that encounter task constructor may execute the task immediately. So that's the original idea when people are going to try to implement it in OpenMP. So that comes with the task constructors in OpenMP. So what it does is it's basically to support irregular programs. So as we said, while loops or loops, you cannot count the iterations. There's no numbers to know for the compiler. The other one is the recursive algorithms, and then for any kind of divide and conquer problems. So tasks actually has been introduced in OpenMP 3.1. However, the compiler supported actually come with quite a later time. There's not actually widely be used. So until OpenMP 4.0 and OpenMP 4.5, they add more control to the task constructor. And now it's actually in good shape, and you can actually use it without problems. So the syntax in task is very simple. It comes with a direct compiler directives. So program, this is in this case, program OMP tasks. So what it does is it created a new task and a task add to task queue, and available thread will pick up one task at a time and until all the task has been done. So to make sure your task has been all completed, and then you can have a sort of control. The other one called task wait. This acts as a barrier, as OpenMP barrier. You can actually let all the task wait and until all finished and move to next. So in 4.5, there is specific definitions and they add more control and some new directives there. So the syntax basically is task. You can have a bunch of different clauses to control it. So the clause could be you have if statement, and also you have a bunch of different data controls as well. And then the task will work on a structured block of your code. So task consists of code to execute and what type of data you want to execute and the data environment as well. And then you can actually have more say about the task groups and the task loop or task yield. You have more control and depends on your applications. We back to that simple Fibonacci examples here. So we can simply apply OpenMP task constructors to the sequential code. So here the main code originally call itself, and then we will run this in parallel. So here we'll create a team of threads to do it. And then we let the master threads here will basically generate the task. And then each thread here will pick up in a core function here. You can say it will use a task. And then each thread will pick up one, and the last will pick up another one. And make sure this two has been done. So we add a task wait here. So once this two has been done, and then we'll return the results it's supposed to be. So here the code itself, I didn't explain to plan to explain it in more detail. But however, in terms of the data structure here, basically when you have the variables defined under the calling function, it's actually local to the calling function. So here, because it's return will be called by the main code, so you need to make it shared and is visible to other threads. So that's the other things, okay? And also for the lists, and originally basically you have this type of code, for example, what I will work to do as a different thing. You can simply apply the OpenMP task constructor. Say you create a team of threads, and here the single will create tasks and put it in task queue. And each one will pick up a task to do. So in this case, it's basically one thread will work on one element on the list, and the other thread will basically keep moving, and one by one, and then when they pick it up and finish the tasks, well, the job will be done at the end. So in this case, it's making this OpenMP can handle this type of applications. Okay. Now we want to move on to a lot of situations. So I want to talk about a little bit about vectorizations. So vectorizations is actually implemented in Intel compiler, and the modern Intel chips all has the vector registers. So if you use Intel compiler, if you say use the optimized, say like -03, it actually automatically enable the vector the functionalities by the compilers. So it does is basically where it's unload the encode way of exploiting data level parallelism in program by applying the same operations to multiple data items in parallel. So mostly it applies to arrays like this type of loop structures. So it's not due by one, and it can launch the multiple operations on different data. Okay. So here is basically is a simple explanations for the vectorizations. So the vector hardware, as we said, Intel modern chips, Intel chips has all the vector registers or vector functional units. So your code, if you compare, and it compare to be vectorized, and it will give you the message say your array is vectorized or not. If it is, it's something, for example, in 4 units in this case, it actually each register will do 1, and the other register can do another 1, and it is basically like it runs in parallel. So OpenMP want to do this type of thing, and then OpenMP, because it's standardized, is not actually bounded by one hardware or compiler providers. So OpenMP they introduced SIMD loop constructors. So SIMD, what you know, is a single instruction apply the same operations to multiple data concurrently. So vectorizations, as we saw just now, is a process of multiple elements of an array at the same time. So OpenMP, if you use this SIMD, is supposed to do exactly the same thing as the vectorizations did by the Intel compilers. Apply to a loop, that's the most widely applications. The syntax is simple as well, and you have the program OMP, it basically is SIMD, and a bunch of other data controls, and then it's basically the for loop. So we have user examples to explain it maybe a little better. For example, here is a for loop, and to do whatever something, for example, the sum of array or whatever, or other operations. And what you need to do on top of this code is basically you add this OMP SIMD. So it does is you work on an array, and it's an array, and actually loop, you cut the loop to chunks, and each chunk will be executed by one vector registers. And by doing so, if you have a bunch of registers, and it will run concurrently. So in this case, there's no parallel, there's no chain of threads apply here. It's basically supposed to do the same thing as the vector, the compiler does. And then you can have working together the SIMD constructors with the work sharing constructors, combine them together. So here basically use the widely used the for compiler for work sharing for the for loops, and you add SIMD to it. So what it does is basically the for basically is divided your loop among team of threads, right? So each thread will work on part of it, and among these threads, where it can cut it what the workload it has to chunks, and each chunk will work by vector registers. It's something like this. So when it does this type of things, right? So this will provide a way to speed up on certain hardwares, like we said on Intel chips, on Intel or other chips or other hardware with the vector registers. Okay. And here, for example, if I have loops in sequential code, and but randomly use a loop, for example, this loop do something, and the other loop will do something else, and this loop will maybe do something else. Or you can have a different approach. For example, if we use the SIMD and also use the SIMD with the work sharing constructor, you can have this type of OpenMP code will work for you. So what you need to do on top of that sequential code is you add the OpenMP and the header file, and what you have, for example, we want to vectorize this loop. We simply use SIMD, and because it's actually do the sum, we can use the reduction in OpenMP. It will do the job for you. And then, for example, this part is basically sort of like initialization, something we simply run it in SIMD. So there is no multiple threads working here. It's basically one thread doing, still will speed up. And then for this part, for example, we use parallel for loop combined with SIMD. And then because it will do some, we still use reductions. So that's the code we transfer to OpenMP, use SIMD. It will be code something looks like this. And you run it. If that index is huge enough, you will see the difference. You can see the speed up. Okay. And then we can introduce the device models in OpenMP. So this is basically an effort to support a wide variety of computer devices. Accelerators these days is very popular, very hot. So like the NVIDIA's GPU or the Intel's Xeon Phi. We know another approach is basically the same approach as OpenMP. It's called OpenACC. OpenACC is trying to run code in threads, that type of way, to work on the GPU and to want to try it in parallel. And now OpenMP want to do that type of thing. And eventually, I think, OpenACC will come to OpenMP because OpenMP didn't have that before. Now he added since the OpenMP 4.0, and then for OpenMP 4.5, make it actually run not only on GPUs, but it also works on all kinds of accelerators, so like Xeon Phi as well. So the constructor name they used is the target constructors. So what it does is actually create a device data environment for the extent of the region, so that when a target data constructor is encountered, a new device data environment is created. and in counting task executes the target data regions. So if the clause is presented and if the device is not available, and then all the jobs will run still on the CPU on the host. So the syntax will take the same approach. Is basically is target, and then you have some clause they can use, like the device. They can actually define to check whether the device is false or true, or what type of device to use. And then it can actually combine with the map. It's basically map the memory and map the data from the host to the CPU or to the GPU. And it can have the if expression as well, a conditional as well. And then there's more to have a data control. For example, I have a target data. This is basically creates a device data environment and execute the constructor on the same device. So this is basically specify the region executed by a device, and the encounter task wait for the device to complete the target regions. And also they have a target update to make sure the corresponding list items in the device data environment consistent with the original list items on the host. And OpenMP distribute is built a loop over team in the Linux, and it also have some others like a declare target, and also they can have teams. It's basically create a team of threads, and where the master threads of each team execute the region, and associate with say the number of teams or the number of threads. So they have some other controls as well. So the execution and the data models is something we listed here. So it's basically the host centric. So the execution of the OpenMP program start on the host device, basically CPU, and then offload target region to target device like a GPU or like whatever other devices. So in principle, target region also begin as a single thread of executions. When a target constructor is encountered, the target region is executed by implicit device thread, and the encounting thread task wait at the constructor until the execution of the region completed. So if the target device, like the GPU or whatever, is not presented, and then all the jobs still being done by the host device, by the CPUs. So if a constructor creates a data environment, the data environment is created at time the constructor is encountered. So, and when an OpenMP program begins, each device has an initial device data environment. So it will basically accept the data mapping. And that's the hard part sometimes when you're working from this. What type of data will run by GPU, and then what type of data will still run by the CPUs. So that's some of things OpenMP right now they have this type of control. The OpenMP, this type of definition is up to the compiler to implement it. So the upcoming GCC 7 will provide this type of support, and under the Intel, the newest Intel compiler also provide this type of support as well. And then the sample code is actually for different accelerators. It could have a different approach. So here is basically provided two protocols. So this type of thing, for example, you have the original OpenMP, the parallel for loop. And if you add this target device, what type of device, and the mapping to from, say, working on this array, and this type of work will load the workload to the accelerators. and this is supposed to work better on the Intel Xeon Phi hardware. And the same type of work tasks, and this type of approach, say you have the mapping, and then you create a team of threads, and then each team will have different work on different part of your code. This type of approach is exactly the OpenACC has taken it, actually borrowed from the OpenACC. So this type of approach is said to work better for the NVIDIA GPUs. So in the future, we hope we have more applications, and then we can talk about some detailed examples, sample code, and we'll see how this can work out and work better for the real applications. Okay, I think that's the plan for today. Is basically an introduction to the three things: the task constructor for irregular applications, for applications not actually fit in the loop structure, and then the SIMD constructor is for the vectorizations, make a good use of the hardware, the newest hardware. And then it's the device models, is basically to try to apply OpenMP to GPU and other accelerators. There is a nice website, it's openmp.org. There's lots of resources and tutorials and some updated news there. And if you click on the specifications, you can find the newest specification. The newest one is OpenMP 4.5. You can see the progress. Task has been introduced in OpenMP 3.1, and then OpenMP 4.0 and OpenMP 4.5 is in much good shape. And then others are basically introduced in OpenMP 4.0 and 4.5 try to make it better. Okay, and if you are interested, you can go to check the links, and we posted here. Some of the slides I also borrowed from, copied from some of them. Okay, thank you.